Have you ever tried to pick out a single specific voice in a crowded room where literally everyone is screaming at the top of their lungs? It's practically impossible, right? Well, in the world of analytical chemistry, scientists face a very similar, incredibly frustrating problem. How exactly do you find an invisible chemical needle in a liquid haystack? Or more specifically, how do you detect incredibly tiny amounts of trace ions when they're floating around inside a liquid background that is chemically noisy and just completely overwhelming? It's a fantastic puzzle. Welcome to The Explainer. Today, we're demystifying conductivity detectors in ion chromatography to see exactly how scientists solve this incredible puzzle. We're going to break down the clever physics and the brilliant engineering that allows us to, essentially, see the invisible chemical world. Here's our quick roadmap for today. We'll start with the ion detection challenge, move into the physics of conductivity, tackle the background noise problem, see how suppressors come to the rescue, and finally, look at some real-world applications. Section 1, the ion detection challenge. Okay, so the basic premise of ion chromatography is actually quite elegant. The system measures polar or ionic species, which are our target molecules, by transporting the sample through a solid tube. We call that tube the stationary phase, and it pushes the sample through using a flowing liquid, which is known as the aqueous ionic mobile phase. The compounds in your sample interact with the stationary phase based on their charge density. So the higher the charge density of your target molecule, the longer it gets stuck or retained on that stationary phase. This is what allows us to separate out a really complex mixture of molecules into individual components, just based on how fast they travel through the whole system. Let's jump to Section 2, Physics of Conductivity. And that brings us to conductance, which is represented by the letter G. Now, conductance is simply the reciprocal or the exact opposite of electrical resistance, and it's expressed in a unit called Siemens. Basically, we're just measuring a solution's ability to conduct electricity. Pretty straightforward, right? To really cement this, think of the contrast between the two. Resistance, or R, impedes or blocks the flow of electrical current. Conductance, G, facilitates that flow. Since electricity is conducted in a solution by ions, fundamentally, if we have a higher conductance, it just means we have more ions present in the solution to carry that electrical current. It's a direct relationship. But here's the catch. To make this measurement actually useful across different machines and different labs all over the world, we use something called specific conductance, or lowercase k. The core equation here, k equals g times the cell constant, acts kind of like the DNA of the machine's software. It takes the raw conductance, G, and multiplies it by that cell constant. This brilliant little calculation normalizes all the data, which allows the measurement to be totally independent of the physical size or shape of the specific detection cell you happen to be using. Now, looking at equivalent ionic conductivities, it's fascinating to see that not all ions are created equal. Different ions carry completely different conductive weights. Notice how the hydrogen ion, H+, at 350, and the hydroxide ion, OH-, at 198, are incredibly highly conductive. I mean, they're absolute heavy hitters compared to a standard sodium ion, Na+, which sits way down at just 50. Keep those high numbers for hydrogen and hydroxide in the back of your mind because they're about to become the villains in our story. Moving on to Section 3, the background noise problem. Let's look at this quote directly from our source material. The difficulty is to recognize in the total signal the part due to ions or ionic substances present in the sample at very low concentrations. So here is the massive problem we run into. The mobile phase liquid pushing our sample through the machine is loaded with highly conductive buffer ions. Trying to detect our tiny trace sample ions inside that highly conductive mobile phase is literally like trying to hear a single person whispering while you're standing in the front row of a heavy metal rock concert. The background noise of the liquid just totally drowns out the signal of the sample. And to make matters even more incredibly difficult, conductance is highly sensitive to temperature. The conductance of most electrolyte solutions increases by about 1 to 2% for every single degree of temperature rise. Because of this, the machine's detection cell requires impossibly strict temperature control, down to 1/100th of a degree Celsius. If the temperature fluctuates even a tiny bit, the baseline noise shifts and boom, our whispered sample signal is lost forever. Section 4, Suppressors to the rescue. Let's quickly map out the physical flow of the instrument in your mind. We start with the pump pushing the liquid, then the injector adding our sample, and the column where the actual separation happens. But right before the liquid hits the conductivity detector, it passes through a device called a suppressor. This right here is our technological hero. Commercialized back in 1975, the suppressor is an absolute game changer. It acts exactly like a pair of high-tech noise-canceling headphones for the instrument. Its entire job is to eliminate the background ions in the mobile phase via acid-base type reactions before the liquid ever reaches the detector. It completely silences the background noise so the sample can finally shine. Remember a minute ago when we noted how highly conductive hydrogen and hydroxide ions were? Well, the mobile phase is often absolutely full of highly conductive H plus and Cl minus ions. As the liquid passes through the chemical suppressor, it physically exchanges those highly conductive ions with less conductive species, ultimately reacting them to form plain old water. It purges the loud background ions, leaving behind a perfectly quiet water baseline. Now, when the target sample ions finally flow into the detector, their conductance spikes clearly against that quiet background. They're finally heard. And finally, Section 5, Real-World Applications. When we look at a successful noise-free chromatogram, the results are just beautiful. This isn't some rare industrial chemical we're looking at. This is the analysis of a simple glass of red wine. Because the suppressor eliminated the background noise of the liquid phase, the conductivity detector was able to clearly chart distinct peaks representing the organic acids naturally present in the wine. Each of those distinct peaks corresponds to a specific trace molecule. The machine successfully detected tartaric acid, malic acid, citric acid, lactic acid, acetic acid, and succinic acid, all hovering around just 4 to 40 milligrams per liter. These are tiny, tiny trace amounts, and they're clearly quantified, all because we figured out how to mute the background noise and let the conductance of the target molecules stand out. So the absolutely crucial point to take away from all of this is that analytical chemistry is as much about removing what we don't want to see as it is about measuring what we do want to see, which leaves us with a final thought to ponder. If a suppressor and a conductivity detector can map out the invisible trace assets hiding in your evening glass of wine, what other hidden molecules, toxins, or nutrients are these incredible machines revealing in the water we drink, the food we eat, and the world around us every single day? Thank you for joining me on this explainer, and keep your curiosity switched on.